So let's get started with the kinematics. Oh, by the way, my name is Jay. Jay. Okay, before we get into the kinematics section, we have a linear setup between, we call it axis definition. We already talked about that in the motion program, before you actually talk about motion program. So you define on one axis, one motor to a certain axis, and in a specific coordinate system. So there are two levels. First, you have to specify which coordinate system you want to work. The second is you define one motor to one axis that's belong to that coordinate system. So different coordinate system can actually have the same axis name, like the x-axis and in coordinate system 1 can be is different than x-axis in coordinate system 2. They have to belong to two different motors, okay? And the motion program is actually execute under coordinate system, meaning the same motion program can actually execute in coordinate system 1, and it can be executed in coordinate system 2, as long as in the motion program, all the axes defined that's already defined in that coordinate system, okay? Like in motion program, you have x something, y something, z something. Then that means if you execute that in coordinate system 1, then coordinate system 1 has to have x, y, z axis defined, okay? The same thing on coordinate system 2. So that's the idea. For the kinematics, it's just another relationship definition between motor and an axis. Before we have axis definition, that's in linear shape, like linear relationship, meaning like this. Let me get this. Before we have this kind of definition. Let's just say I put that in coordinate system 1, percent 1, and I do pound 1, 1000x. Something like this. This is what we call axis definition, and there's a linear relationship between the motor and the axis you define. So usually the unit in motor side, on the motor side is in counts. On axis side is user unit. Might be millimeter or inches or whatever, okay? So this is the scale factor that's between the motor counts and the user unit you are going to use, okay? That's basically the idea. So the kinematics comes in because sometimes the relationship between the motor and the axis are not linear. You cannot actually just use a constant value to actually express the scale between them, the relationship between them. So that's why we need kinematics. Let me talk about this a little bit. If you have something like this, is this legal? Is this correct? Should be, right? But yes and no. Mathematically, it's correct. But in the real application, this is not correct. The reason I say that is because you have to have another motor that's defined in the same coordinate system with a different scale, for sure, to actually make this one work. Okay? The reason for that is, in the beginning of the motion program, when we talk about motion program, you actually have x something, y something, z something, right? So that means your command is actually in terms of axis. Meaning, if you say, in the motion program, say x1, y1, you want the motor to go to the axis to go to x1 and y1. That means this is 1, and then we calculate the motor position for you, right? But in the beginning of the motion program, I have to know where the axis is, right? You have to use, PMAT has to use the motor position to actually calculate the current axis position before you actually execute the motion program. So I know the first move, how to actually do the trajectory. If this is the first command you have in the motion program, then PMAT has to know where you are right now through the current motor position. Okay? So, imagine this. If you only have the first one, you know where motor 1 is. How do you calculate x and y to actually tell PMAT where my axis is right now? You can't, because this is just one variable coming in, and you cannot calculate two of them as the result. So, by definition, you have to have another one to actually say, okay, this is a relationship. And they use these two as an equation, which can be simplified as this. Motor 1, motor 2 counts equal to this. X and Y. Okay? This is a relationship, linear relationship. So this matrix has to be invertible. So I can actually, from my motor position, calculate the axis position, and vice versa, I use the axis position, calculate the motor position. Okay? So when we talk about the axis definition, we actually give you a huge, giant matrix, right? Because one coordinate system can actually control up to 32 axes under one coordinate system. So we have a giant 32 by 32 matrix to actually say, okay, this is the calculation that we want to use. Okay? Once you define the axis definition here, we actually put these variables in that matrix, and then we do the inverting of the matrix to actually calculate from motor to axis, from axis to motor. Okay? This idea should be correct. Should be understand right now. Okay? So, basically, kinematics is the same idea. It's just, okay, this relationship here is nonlinear. I cannot put that into a matrix. So we have to define it in another way. So we use a subprogram called forward kinematics program, a subprogram, and inverse kinematic subprogram to actually say, okay, if I want to calculate from motor position to axis position, then I use forward kinematics. If I want to calculate from axis position to motor position, I use inverse kinematics. That's why we have this here. This is the idea. So, as you can see here, the kinematics is just a relationship between the tooltip coordinates and the matching position of the actuator, which is the motor, or the joint, or in your robot. Okay. These are the variables that we reserved for the kinematic calculation. These are all local variables. You don't have to worry about the numbering, like what's the L variable, what's the C variable, because initially we actually define the axis name for them, or the variable name for the axis and motor. So you just use the names. You don't care about the local variable. Okay, so like I said, for kinematics, it's actually from motor to axis position. From motor unit counts into engineering unit, the user unit. The local variable for the motor are from L to L max minus 1. The max number is what's the max number you can use in your coordinate system. Okay, we have a system.variable structure. That's for that. I'll introduce that later. On the other side, we have a C variable, which is defined as king pulse axis with alpha. Alpha is like ABC, XYZ, UVW, something like this. Okay? On this side, king pulse motor X, that X is the number, like motor 1, motor 2, motor 3, up to 32. Okay? Any questions so far? that's the basic idea for this. And then later I'll introduce how do we actually set it up for this forward kinematics and inverse kinematics. I'll actually provide a template for each, and then later you just put your calculation equation into it. That's it. Okay? Okay, so there are a lot of tweaks in the kinematics, but these are the basic template. So you just say open forward, just like the open PLC or open prog for the program, motion program. You say open forward. This is not really necessary, but we usually actually indicate that which coordinate system you are using for this kinematics, because you can actually have up to 128 different coordinate system. And so you have to know which kinematics is used by which coordinate system. That's why you have this label. Okay, so open forward with the number of the coordinate system and close. These are the content here. The same thing with inverse kinematics. Okay, the setting on the axis, since right now we're not using the axis definition like that, then you have to do something else. This is what we do. So pound x, this x is the motor number, is defined to an I, which means the inverse kinematics. Okay? And the segmentation time has to be greater than 0. This is how we actually calculate the trajectory. Okay? Like if you plan a path, then this is the segment that we actually put. Like if I have a 1 second move from here to here, from A to B, this is the segment time. This is in millisecond. This is how many milliseconds I want to chop in that 1 second. And that's how fine that will define the path, how I actually calculate. Okay? And that's important for kinematics, because if this is 0, then kinematics is not working at all. We won't calculate that for you. Okay? Any questions? Okay. So let's come to the setup for the forward kinematics. As I just said, for the forward kinematics, the input is the motor position. And this is in local variable Lx. X is like 0, 1, 2, 3, 4, 5, up to 31. But this x is limited by this structure. It's system max motors. This number is usually set up to a number that's minimum for your how many motors you want to use. The reason for that is power PMAC can actually control up to 256 motors at the same time. Okay? For the synchronized motion, which is in the same coordinate system, is 32 motors in one coordinate system. Okay? Which means I have to prepare all those buffers to actually say, okay, motor 1 setup is what? Motor 2 setup is what? So I have to prepare that. So you have to set this one up to a minimum value for your system to actually reserve all those buffer, which you may not use, because like motor 255, you're not using. But if you didn't actually set this number low enough, then we actually prepare that for you. Then that's not used, so that's wasted. That's why we have this system max motors number for your definition. Okay, in the IDE, the king pulse motors. Motor X are automatically assigned to this Lx. That's why I say that in the kinematics setup, in the subprogram, you use the variable name instead of the variable like X, Lx, or C, 0, something like that. Okay? The output is the axis pointer. Local variable C0 to C31. Like I said, we have 32 motors in one coordinate system. But again, they are not all used, right? So that's why we have another variable in here called king axis used. This is automatically defined, and it's designated to D0. And you have to give me this to actually say which axis you are using. Okay? We have a table here. If you're using X, Y, Z, and C, that means you have to X, Y, Z, and C here. They're actually defined as the bit value here. So C is $4, X, Y, Z is 80, 10, and 80, 100, and 200 in hex. Okay, so you add them together. You tell them, okay, these are the bits that you want in that 32-bit register. Okay, these are the bits that will be masked, and these are the axes you want to use. Okay, so in IDE, the variable king pulse axis alpha is like X, Y, Z, or ABC you want to use, automatically assigned for the king axis used that you have in here. Okay? So far, everything good? Okay, so more detail in this. For forward kinematics, it's not used only for the motion program when you actually have a trajectory, but also you can actually use it as a query. Like, I want to know what's the axis position right now. Then you have to run your forward kinematics one time, because it will actually calculate from the current motor position to actually give you the axis position, right? So that's why we actually have this function. If you query the axis position online, that's the n%. This x here is the coordinate system number. So if you say n%1p, it will actually list all the axis position for you if you actually have defined something. Okay. Here are some other things. Query the axis velocity and query the axis following arrow. These require something else other than just the current position. Meaning, if you want to know the velocity of the current axis, then I need at least 2 positions to actually calculate the velocity, right? That means you have to pass through your forward kinematics at least twice to actually get it, right? So we have this double pass structure in here in forward kinematics. If you don't want to use these 2 online command to actually query the current velocity or the current following arrow for a specific axis, then you don't need this. But usually, you don't really know in the future if you want to use it or not. So we usually put it in here in the template for the forward kinematics. Okay, so this second pass is actually using a cosub function in here. This will actually cosub 100 means that I go to 100 line label as 100. It's the similar thing we talk about in the subprogram. So here we have another variable. It's called king val enable, meaning if I want to enable the velocity calculation or not. Okay. If it's greater than 0, with this value is like not if it's not 0, it's 1. Okay. So when you actually activate the online function, want to query the velocity, you will change it to 1. Okay, and then jump to this n100 line and then do the calculation. Okay. The reason for that is this one king axis used. Like I said, this is already defined, right? If you want to actually have this, you have to define your axis used in your kinematics. So you don't have to run this one again. You just jump through it and then run twice. Run the second time. So I actually get the difference between this time and the previous time to get the velocity. Okay? So this is a little tweak in here. The other thing is, since the motion program can be, this function, forward kinematics function, can be called from a motion program because when you execute the motion program, we automatically call the forward kinematics. Or it can be called by the online program. So we want to know from where you call the forward kinematics because we have to do something related to that mode. This is a bit in here. It's ldata.status. If it's equal to 1, that means the forward kinematics is called by a motion program, which is usually the case. Now when you execute a motion program. The second one is if it's 0, then it's being called by a query command. That's an online command that I listed here. Okay. How do we use this? With this bit, you can actually abort the program properly, which I'll explain later. The condition for stopping the calling the for kinematics is under these conditions. One is the home complete status bit, meaning if you want to execute your for kinematics, I have to make sure that you already home all the motors. Otherwise, whatever is in the motor position count, I will consider that's the correct position that got referenced. If you have like a robot, then you have to define your 0 position, right? That 0 position doesn't really mean that's the 0 encoder counts. There might be some offset, or depending on how you actually home the motor, then there might be a different 0 position that's defined in the mechanism in your robot arm. So you have to make sure that already happened and motor is homed. So I know that the calculation through the for kinematics will be correct. Okay, that's the first thing you want to check. The other thing is, if it's like not home, then I want to exit for kinematics. But I have to know where I call the program. If it's a motion program, I will actually say, okay, it's the same thing as abort command if you set this bit, this status value to 255. Okay, that's an error bit that we have in the motion program execution. Meaning, if you execute a motion program but nothing really happened, then for a long time, then maybe there's a less buffer for you to actually execute the motion program. Then we say there's a runtime error. That means it has been passed too much time and there's nothing happened. There must be something wrong. Then I set this bit. This is in the motion program, that's abort. The other one is, if you are calling from the query command, then you're not executing anything, right? But if your motor is not home, then that means your query will be wrong, because I cannot do the forward kinematics for you to do the calculation. So I send another, I send the illegal number, which is like square root of -1, which is not a number. Then I'll actually output that. Okay, these are the 2 status that we have. So this is just prepare you for the template. Okay, for all the functions that we have offered in for kinematics, which is this. So basically, this is the most important slide in for kinematics. You just copy and paste this, and then you put your equation in here, and that's it. Okay. Let me go through this again. So first you have this double pass function in here. So you do if king val enable call sub 100, and then this is the king axis used. Here I only use x and y. So you actually get the hex bit number together, add them together. This is the number with the x and y. Okay. If coordinate system 1 dot home complete. This is a very good, very useful structure. It will actually check all the motors that's defined in that coordinate system if they are homed. If not, then this bit is 0. If they are home, then the bit is 1. So you don't have to check motor by motor that's defined in that coordinate system, because otherwise this will be very long, like motor 1 dot home complete bit, motor 2 dot home complete bit, then something like that. We have a coordinate system bit to actually check the status in this coordinate system. Okay? If that's complete, then I do kinematics. Else, that means it's not home. The for kinematics calculation will be wrong. Then I check where you call this function. If this is 40, then that means it's called from a motion program. I set the coordinate system error bit to 255. If not, then that means it's called from a online query command. Then I output not a number value into the king axis position. Okay? Any questions so far? Okay, good. So this is the template for that, and then this will actually offer you all the functions that we have inside Power PMAT for kinematics. So the inverse kinematics is easier. It's the reverse side of the forward kinematics. So the input for that is the axis position, which is defined in C0 to C31. But since you already have the king axis use defined in the forward kinematics, then these should be all the axes you want to use over there. Okay? The output are the motor position. Okay? The variable is the same as before that we defined king pulse dot motor x. King pulse motor x. Okay? So remember, when you actually write the equation in forward kinematics, inverse kinematics, you have to make sure that you understand which is the input, which is the output, because at the end, for inverse kinematics, I will gather this. I will get this value. I want this value for my calculation. Okay? There are some other axes other than the, well, I should say in all the 32 axes that we have in one coordinate system, we have the linear system, linear axis, and the rotary axis. Rotary axis are these: ABC and AABBCC. Okay, the linear axis still got two groups. One is the Cartesian axis, is XYZ, XXYYZZ, UVW, UUVVW. Okay, so we have like 4 different sets of Cartesian coordinate system. For the rotary, you have these 2. Okay, the special thing for these axes is this can actually define a rollover number for that. Meaning, usually what we encounter is if you just a rotary motor, then if you want to actually go from let's just say you have a rotary axis, A. This is 0 degree. This is 180. Something like this. If you have a motion program, say A1, that means, well, if it's in degree, then that will go to here, right? 1 degree. Here. But if the next line is like 364. No, sorry, my fault. It's not the year. 59. Which is in here. Right? Should be. But usually when you actually look into the number in here, what will this do? This will go forward, right? Because this is 1. This is so big a number, then I have to go this, in this way, right? To get it here. Right? But if you just want the position, then the best way to do this is in here. 2 degree move instead of 358 degree move, right? So this is what we do in rollover. So for these axes, this is a special function. If you define what's the range of this rollover, usually it's 360 if it's rotary, then we'll do that move for you directly. Meaning if you set up the rollover in this A axis, then this move in here will be the shortest path of the motion you define here. Okay? So even though you actually have like multiple turns and everything, something like that, then we will actually find the shortest path for you. And this is sometimes very useful for a certain application that will actually don't want to deal with the multi-turn stuff. Okay? But this function is only related to these axes. So just for these 6 axes. Okay? Other than that, the inverse kinematics also got the constraint. Like in forward kinematics, I have to check if my motor are home, it got reference. In the inverse kinematics, usually what you encounter is what's the workspace of your robot. You have to define a range. Otherwise, this range will be like wherever, then that's probably outside your definition, then that probably won't work. So you have to contend that first. So to ensure that whatever axis position that you put into the inverse kinematics will get a meaningful result for the motor position. Okay? We will actually talk about an example later. That's a SCARA robot, two-arm robot that's on a plane. Okay, so you have to define that first. Okay, so for the inverse kinematics, the template is easier. It's like this. Usually we will actually get a Q variable for the flag, so we know that there's something wrong with kinematics. You don't need to do that, but it's usually a standard practice. Okay, so open inverse. If the workspace constraint is valid, then I keep my calculation in here. And then I set this flag equal to 0. That means, well, it's doing the kinematics, inverse kinematics calculation. If not, then I put this value into 255, which will stop the calculation for kinematics. And I put this flag to 1. So externally, you can actually observe using this bit to actually do whatever necessary afterwards. Meaning, if it's not home then or something like that, then if I see inverse kinematics 1, then I actually go back and home the motor. I check the status for all the motors in the coordinate system to see what's wrong. Okay? So this is it. Any questions so far? So kinematics is not really hard. It's just like the same concept as the axis definition. It's just we don't have a linear relationship, so we cannot put just a matrix over there to actually do the converting between the axis and motor. Okay? So it's your responsibility to make sure that whatever put in here for the content for inverse and whatever put in the for kinematics are one-to-one mapping. Okay? Usually you will encounter for the series link robot, what you will encounter is for one specific axis position, you will actually have multiple solutions for your motor joint. Okay? For forward, it's easier. The forward kinematics for that it should be like one-to-one. But for the inverse, will be multiple solutions. If it's for a parallel robot, that's the other way around. The forward kinematics will actually have a multiple solution, usually. And you have to determine which one is the correct one. The inverse is actually easier. Okay? So you have to make sure that you have the logic that's inside. Make sure that the mapping is one-to-one. Otherwise, because we're getting the position out of forward kinematics, and that's the first position feeding into the inverse. If that's wrong, then the calculation will be wrong. Then you don't know what will output to the motor for the move. Okay? Okay. So this is our example. This is a two-arm linkage SCARA robot, and for forward kinematics, let me define the axis first. So the first thing you have to do is define your axis, meaning if the tooltip is on a plane like this, then of course you can define x and y, but you can define something else. If it's a 3D robot, then you have to define x, y, z. You have to define what you want to calculate as the axis position. Okay? Intuitively, it's like x, y in here, but some like the 6-degree robot, then you have to determine how you want to define your orientation. Okay, is you through Euler angle or something else, then you have to define that. Okay? So the first thing is identify the axis you want to use. And in forward kinematics, the input is axis position, motor position, right? Here, we are using angle here because in here, this is one motor, this is the other motor. The motor rotation angle counts can be represented into angle. So there's another relationship between this A and the motor counts, okay, which is linear. But this motor position, if it's the angle here is not in a linear relationship with the axis position. So you have to use kinematics. And this is the equation that we have. Okay, for forward. Okay, for inverse, that means the input is the axis position, the tooltip position, and you have to back calculate what the motor angle is for this case. Okay, there are two solutions for those inverse kinematics. For a specific position, this is y-axis. For a specific position x and y, you will have two solutions. One is this, the other one is this. Okay? The same arm length, but different angle. Right? So you have to decide which one you want to use, or under what circumstances you want to use which one. So there's a logic that's in here. In here, we simplify the whole thing, so we use the right-hand one, meaning here B, I take the positive solution of this arc cosine value. Okay? See here, the value of this angle, this is A, right? And this is B. So in this direction, it's the right-hand row, this is the positive, right? This one, this angle is positive, right? But this angle is negative. So this V value will be negative. So in the math, you actually see, okay, the two structure, the two attitude that we have in here is because of this one. Okay? So we choose the right-hand one as the positive one, and then we use that to calculate A. If you have a negative one, then you have a different A in here. Okay? You can have two sets, depending on which one, under what condition, which one you want to use. But here we just simplify things. Okay? You can imagine that this is just a simple two-bar linkage robot, and you got two solutions. If you have like 6 degrees of the articulated arm, then you will have like multiple solutions for this. And you have to determine which one is the good one for the curve calculation. Okay? So, we have the equation here. So we will put this equation in for kinematics. We'll put this equation in inverse kinematics. Here, the other thing. The arm length that we define is 400 and 300, which means uh, 400, 300. The arm span length will be 700, right? That means it's confined in this circle. 700 millimeter circle. Okay, the tooltip range. The other one is, if it's minus 300, here, then this will be 100 circle. This is the place that the tooltip cannot reach. Okay, so the work range is in here, in this disk, or dome, whatever you want to call it. Okay, you have to find that first. But how do we do that? Let me see. So let me introduce the forward first. I will explain this once, and then later you can actually put the code into your PMAC, and then you will see how it works. Okay. The first part, usually we actually find all the variables that we want to use in the calculation. So, like the coordinate system, CS global, these are the coordinate system specific variable that you define in this coordinate system. And then you give it a number. This length 1 and length 2 is the length of this two arm. So this is the structure of the robot. You have to define it first. This is count per degree per count. This is actually for later calculation. It's easier. We like multiplication. We don't like division. Multiplication is actually faster and no problem. With division, if you divide it by 0, then you will get a problem. Okay? So that's why we define these two. Scale factor first. So this is the definition for your robot structure, and then you put that into core kinematics. Like we said, double pass rule here, and you define your axis, what axis you want to use. Check if the motor are home, and then you put the kinematics in. So you can see here, The input are motor 1, king pulse motor 1 and king pulse motor 2, right? That's the input. The output will be the king pulse axis X and king pulse axis Y. Okay? Here's a 90-degree thing in here. Okay? I want to explain that a little bit. Because in the initial program formula, that we don't have this 90 degree. It's just A plus B, A plus B. Right? And yet we have a 90 degree here. This is A. This is A plus B with the 90 degree. The reason for that is this is your robot. This is the tooltip. If the tooltip is on 700, is it valid solution? It should be, right? Because this is on the ring, although it's on the line, right? But remember, this is a computer. We got a floating point arrow in here. So if here I use this value in here, and then I calculate 700.0001, what does that mean? This will be outside the range because this is outside 700, right? Because that's the calculation that through Kinematics, the floating point. After the Kinematics calculation, then I calculate this. This is the result. But although we know that this is okay, but for a computer, for PC, this is not okay because this definitely actually violates the range definition. Okay? So that's why we put the robot initial position in here, which is adding 90 degree in here to make sure that initially, if your motor at home, then if you go to 0, 0, something like this, then this will be the position that you will have. That's within the range, no problem with inverse and forward kinematics. Okay? So when we actually get into a little bit more detail, the concept of forward and inverse kinematics are easy actually, but the details, that's what you are looking for. This is one of them. Okay? So that's why we add 90 to actually make sure that the initial position is there, instead of just flat, 0 position, stretch out. Okay? Okay, so you have to do the same thing in inverse. This is just forward, right? So this is all the template, this is the equation, and otherwise, if it's called from the motion program, then this is what. If it's not home, this is called from the online query command. If it's not home, then you upload this. Okay? The inverse kinematics. First, you have to define, well, you should already have this already. That's for the kinematics. But for kinematics, doesn't really care about this. For kinematics, you just use the motor position to calculate the axis position, right? For the inverse kinematics, you have to define this first. Okay? These are auto-defined. I still listed here. But once you have the axis used, king axis used, this is automatically defined. These are the variables that I'm going to use in my inverse kinematics calculation. And this is some value that's using the length. See here, this is a length, a square plus sum together, and also some other thing. Okay? This is just to save your time for the calculation. Okay? Because since the lengths are defined already, then these should be fixed. This got another benefit for you. So if you have another robot that got similar structure but different length of the arm, you can just change the variable in here, value in here, and then this will run still. So the actual limit that I have on that is 1 degree. So it will be like smaller than 700, and it's bigger than 100. To make sure that I can get the quick calculation without the floating point going outside the range. Then you calculate this, and the output is in here. See, King pulse motor 1, King pulse motor 2, is the output for the inverse kinematics. That's what I want. If it's outside the range, then I'll tell you, okay, there's something wrong. Okay? This will happen when you say, okay, if I say I have a command, x 800, y 0, which is in here, which will be rejected. Okay? That's why I say that you have to set it up. Otherwise, this will actually calculate something for you, which is the complex number, and I don't know how Kinematics handle that as the motor position. Okay. Questions so far? Okay, let's try this. Before that, position report. This is usually for like the HMI. Like I want to move my robot, but I really want to know where it is right now instead of just online query at the same 1P. Then this is the PLC that we use. Okay. The reading is actually through the P read is actually the actual position for the axis. The D read is the desired position of the axis. So there might be some difference, but usually we just do the report in here. So later, if you want to plot the trajectory of your robot in full football, then you just plot these variables, and you will see the trajectory. Okay. Okay. The other thing for this is actually within motion program, all the variables that's inside are local, so you cannot extract that out. If you don't use this, you cannot actually get it out. Because, well, they are all local variables, so the global status, you cannot see it. Okay? That's the reason why we want to use this. To actually extract that out to a global variable, then you can actually plot this. And we have a little program in here to just draw a box. And this is the desired position, this is the actual position. If the tuning of your motor is like crappy, then you actually see a significant difference between the desired position and the actual position. Here is just like, okay. So now let's put this to PMAC and then see if we can actually replicate this. Remember, you have to put all the code. This is in forward, right? This has to be all in forward, including this one. This. In inverse, you have to put all these in inverse kinematics to actually download it and make it work. Okay?